So what we're going to consider now is the magnetic fields around straight line currents. Now, we have seen the equation previously in Physics 1b for the magnetic field around a straight wire carrying a steady current, and it's given by B is equal to mu naught I divided by 2 pi r, where r is the distance from that wire. So I've sketched here what this magnetic field looks like. In this case, the current is shown by the red dot and it's coming up out of the screen. And we're going to call that direction the Z direction. And so the magnetic field loops around and drops off as 1 over R, as I've tried to draw here. So one thing that you can hopefully kind of intuit just by looking at this diagram here and what we know about div and curl is that the divergence of the magnetic field, we would expect this to be equal to 0, just because divergence tells you if something's exploding from a point. So to have a divergence, we need to have some kind of radial vector there, and there is none here because they're all looping around in nice circles. So this isn't a proof of this, it's just what we'd expect intuitively from looking at this diagram. Also, from looking at this diagram, we'd expect that unlike for the electric field, we'd expect the curl of the magnetic field to not be 0 because it is looping around. And intuitively, curls tell you how much something kind of swirls around and wraps around the origin like this. So it'll be useful to also picture this, looking at it from another angle. So this situation are exactly the same. It's just in the top one up here, I've got, this is drawn in my y plane, and then down here I've got my x-axis going like this, and I've got my magnetic field lines here looping around in the xy plane. And just a note, they are looping around the same all the way up and down the z-axis. This is independent of z. It was just simpler for me to draw them at the one point, so I did. But the magnetic field line up here is, if this is like a point along the y-axis, is going into the screen in the xy plane, the same as it is down here. I just haven't drawn it there. Okay, so what we are going to start by doing is calculating the magnetic field around a closed path. So let's take a closed path like this one here. There's my path. And I know that my, let's say this path here, let's let that have a radius of S. So I know that my magnetic field strength is given by this relationship here. So this will be equal to mu naught I divided by 2 pi. In this case, it's S because we've let our path have a radius S. And then I need to times it by that path length, which is just dl. Okay, so what I can do is pull everything out the front because everything here is fixed. I'm not varying my path radius at all. I am just working out what it is around this fixed path. So this is going to be equal to mu naught I divided by 2 pi s. And then I'm taking the integral around this path. So physically what this means is it's this path length here, which is just the circumference of this circle. So this is going to be equal to mu naught I over 2 pi s times the circumference, which is 2 pi s. These will cancel out, and this is equal to mu naught I. So notice how this ends up being independent of S, and that's because my magnetic field strength decreases on 1 on R, whereas the contribution from the path length increases by that same amount as 2 pi R. Now, this was derived for a very specific case where we were taking a circular loop around an infinite straight line current. In order to come up with a slightly more general solution, it'll be helpful to move to cylindrical coordinates. So let's move to cylindrical coordinates where we've got S, which is the distance from the origin. So just down here, let's start by taking the same path. So let's draw this same path here. S is just this distance from the origin, exactly like it was up there. And then we've got phi. And phi, remember, is the angle measured from the x-axis. So phi is measured around this way, but it's measured everywhere going around. If we're looking down from the z-axis, this is going anti-clockwise around from that x-axis, and then we've got z, which is just our distance from the origin on the z-axis there. So remember that our little increment of length in cylindrical coordinates is given by dl is equal to ds in the s direction plus s d phi in the phi direction plus dz in the z direction. Now we're going to need to work out what B is in cylindrical coordinates. You can see that the magnetic field lines are always parallel to this phi vector. So B is going in the phi direction. So in cylindrical coordinates, we can write, well, B is equal to mu naught I over 2 pi s, and then this is in the phi direction. So we times it by a unit vector in the phi direction. Okay, so let's start with the same loop we had up here. So we'll start with a closed loop, but then we'll be able to generalize it more easily in cylindrical coordinates. So we're working out what this is around that closed loop. So we can write that as mu naught I over 2 pi s, and that's times phi. And then we're taking the dot product of this with dl here, and this is dl. And since B is only in the phi direction, we're only going to have to worry about the phi component here. So we can write this down as s d phi phi. So we're taking the dot product between these two things, and when we take the dot product, we end up with mu naught I over 2 pi s times s d phi. You can see the s's cancel out, and now what we can do is pull the constants out the front. So mu naught I divided by 2 pi, and then it's just the integral with respect to d phi, and in this case it's a closed loop. That's what this circle means. It's a closed loop, and so we're starting at phi equals 0 and we're going once around, so that's to 2 pi. So we can put this is from 0 to 2 pi, and this is equal to mu naught I over 2 pi times 2 pi, which is equal to mu naught I, which is what we would expect because it was just doing the same thing here, but in cylindrical coordinates. But what this allows us to do now is consider what B dot dl is going to look like around a few different paths. So, for example, we could choose a path. Let's do a purple path, which is something like that. And in this path here, we are going from phi 1 to phi 2 and then back to phi 1. So it's going from phi 1 to phi 2 and back to phi 1 because it was only, according to this dot product here, the phi coordinates that we have to worry about. So around this purple path, we can put that the integral of B dot dl is equal to, we'll have the same constants here. It's just the limits on our integral that are going to be different. So I am going to skip to this step here, and we know that we've got the constant mu naught I over 2 pi. And then we've got our integral over d phi, but we're going from theta 1 to theta 2, and then because it's a closed path, we're going back from theta 2 to theta 1 d phi. And so you can see that this is equal to mu naught I over 2 pi times the integral theta 2 minus theta 1 plus theta 1 minus theta 2, phi, sorry, I'm saying theta, but I mean phi. And so this, you can see that this phi 2 cancels this phi 2, and this phi 1 cancels this phi 1, so this whole thing here is 0. So this is going to be equal to 0. So when we've drawn a path, like we have with that little kind of lavendery purple path that doesn't include any current inside it, we've ended up with 0. And if we considered going around this loop twice, so going from phi equals 0 to 2 pi, and then going again from 2 pi to 4 pi, then you can see that our limits on the integral here are going to be from 0 to 4 pi, and we'll end up with double this. So if we loop around twice and contain that current twice, we're going to end up with double this path integral. Now, as well as changing the path that we're integrating around, we could imagine what happens if going back to this original loop here, rather than just having this one current here, we added in a few more current carrying wires. So what happens if we have one which is going kind of up like this, and another one which is going, say, up like this? And so these current carrying wires are all included inside that loop. Well, we've seen that the distances cancel out. So it really doesn't matter how close this wire is to the edge of this loop. What matters is if it's inside it or not, because we saw with this purple path, if the loop was outside the wire, then it didn't contribute. Well, in this case, each of these pink wires is going to contribute the same as the red wire. And so our current here is going to be the sum of the currents in each of these wires. So this gives us Ampere's law, which tells us that the integral around a closed path is equal to mu naught I enclosed. Okay, so this is called Ampere's law. And let's put a purple box around it because it's important. Right, so now what we can do is remember back to what we learned about currents, and the current is equal to the surface integral of the volume current density dot dA. So we can write down that this enclosed current here, which remember can be lots of different currents. So it can be this situation where we've got all these straight line currents which are going through our closed surface here. This is equal to the integral over that surface, so it's a double integral because it's a surface integral of j dot dA. And now what we can do is combine Ampere's law with this to write down that b dot dl, so that's the integral around a closed loop, is equal to mu naught times I enclosed, which we've said is the surface integral of j dot dA. And then what we can do is use Stokes' theorem, which tells us about the integral around a closed loop. So in this case, we've got B is our field dot dr. So this is equivalent to this. And so we can write this down as this is equal to the integral over that surface of the curl of B. And then remember that this is a unit vector in the n direction times the surface area of that little increment. So we've been writing that as dA. It's the same thing. And then you can see by comparing this term and this term, if we put the mu naught inside here, which I'm running out of space to do, you can see that we must have mu naught J is equal to the curl of B. So that's an important relationship as well. And it agrees with our intuitive understanding up here that this curl for the magnetic field cannot be zero, and it starts to give us a way to calculate it. Now, there was a big assumption in this. We were assuming that we had infinite straight line currents, which obviously is not always the case. In fact, it's often not the case, but as it turns out, a lot of things can actually be approximated this way. So we will now do a more formal derivation of this, but hopefully that's given you a good understanding of where this comes from. So what we're going to do now is more formally come up with an expression for the divergence of B. So we've said that we expect this to be 0. We're going to start from the Biot-Savart law, where we're considering the volume current density, and so this is a three-dimensional volume integral. So this equation was copied from one of the previous sections where we wrote down our Biot-Savart law for the current densities. Okay, so in order to do this, we need to have a very clear understanding of exactly what each of the terms in this expression means. So let's start by drawing a diagram. So let's imagine some area of space here with a current density flowing through it. And we are going to consider a little increment in this volume of space here. This little increment is located at x prime, y prime, and z prime. And it has a volume, d tau prime, equals dx prime, dy prime, dz prime. And we'll call this location r prime. So r prime is x prime, y prime, z prime. And then what the Biot-Savart law says is that we're measuring the magnetic field at some location R. So that's some place up here. This is location R, which is equal to X, Y, and Z. And we are measuring the magnetic field at this point. Now, J, that is the current density going through this location here, and our curly R is the vector that points from R dash, the point where the current density is, to the place where we're measuring the magnetic field. So our curly R vector is this vector here. So let's write down formally what everything is, and I'll try and color code it a bit to the diagram. So B is a function of X, Y, and Z because it depends on where we're measuring it. So it's not a function of these primed coordinates. It doesn't matter what this current density is. B is going to depend on X, Y, and Z. J, on the other hand, is a function of X prime, Y prime, Z prime. So it depends on this. It doesn't matter where we measure this magnetic field. That doesn't affect the current density through this location here. Curly R is we can write it as equal to x minus x prime in the x direction plus y minus y prime in the y direction plus z minus z prime in the z direction. And what we're going to need for some of our calculations, that's the r vector, because that's a vector, is we will need, because we've got it in this integral up here, we'll need r squared, and that is equal to x minus x prime squared plus y minus y prime squared plus z minus z prime squared. And we're also going to need the unit vector in the r direction. So in order to get that, we are going to need to divide r by the absolute value of r. So we will have that r hat vector is equal to we've got curly r divided by the absolute value of r, which is just the square root of r squared. And so we can write this down as x minus x prime x hat plus y minus y prime y hat plus z minus z prime z hat. That's hat, not prime. And then we need to divide by the square root of x minus x prime squared plus y minus y prime squared plus z minus z prime squared. And d tau in this thing we've written over here. It's dx prime, dy prime, dz prime. Now what we're trying to do is find the divergence of B. So that's what we're going to do now. And we're taking that divergence with respect to where it's being measured from. So x, y, and z, not with respect to x prime, y prime, and z prime, which is where our current distribution is found. So we are going to take the divergence of B. We've got B up here. So we're taking the divergence of this thing. Because mu naught and 4 pi are just a constant, I can just bring them out the front of my divergence. And so I can put my divergence just inside this integral here. So we can write this out as mu naught over 4 pi times the integral of the divergence of j cross r over r squared d tau. And now what I'm going to do is use one of the product rules. So Griffiths has this listed as product rule number 6 in the front, which tells us that the divergence of the cross product of two vectors is equal to the dot product of one of those vectors with the curl of the other minus the dot product of the other vector with the curl of the other one. So let's write this out as this is equal to mu naught over 4 pi times the integral. And now in this case, J is A, so this is the current density, and R hat over R squared is equal to B. So we've got unit vector in the R direction divided by R squared, dotted with the curl of J, and then minus, we've got J dotted with the curl of R hat over R squared, and then we've got d tau dash. Okay, now what we can do is consider these two parts separately. First of all, let's consider the curl of J. Now, remember when we were taking the divergence, this was with respect to x, y, and z, the position where we were measuring the magnetic field. So that means that this curl is with respect to x, y, and z. But J, that is the current density, and it's independent of where we measure it from. So this is independent of what we're taking the derivative with respect to when we take the curl. And whenever we differentiate something which is a constant, we just get 0. So that tells us that this is going to be equal to 0 as J is independent of X, Y, and Z. So that means that this whole term here is going to be 0. So now what we need to do is worry about this term here. And I think probably the easiest way to do this is to just write it out in full. So let's write it out in full over here. We've got the curl of curly r hat divided by r squared. And this is equal to the discriminant of x, and then in the y direction and in the z direction. And we've got d dx, d dy, d dz. And then we've got our hat vector here, and we're dividing it by r squared. So this whole thing, this is going to be equal to x minus x prime in the x direction, and then it'll be divided by, on the bottom, we've got this times this. So this will be divided by, let's put it as curly r to the 3 on 2, where curly r to the 3 on 2 is equal to the square root of x minus x prime squared plus y minus y prime squared plus z minus z prime squared. And in the y direction, we'll have y minus y dash. Oh, sorry, I shouldn't have added that vector in there because we're inside here. Divided by curly r to the 3 on 2. And here we've got z minus z prime divided by curly r to the 3 on 2. Okay, so we need to work out what this determinant is. So it is going to be x prime times d dy of this minus d dz of that. And then we'll have the y terms and the z terms. Let's just look at what happens with the x terms, because you can see there's a whole lot of symmetry here. So by understanding what happens with it in one of the dimensions, I think it'll be pretty clear what's going to happen in the other one. So we can say let's just take the x component of this. This is going to be d dy of z minus z prime times x minus x prime squared plus y minus y prime squared plus z minus z prime squared. And this is all to the minus 3 on 2. And then we've got minus d dz of y minus y prime times x minus x prime squared plus y minus y prime squared plus z minus z prime squared. And this is again to the minus 3 on 2. So now we're just doing these differentials here. Z minus z prime is independent of y, so we can bring that out the front of the derivative. And then what we're doing is taking the derivative of this lot in here with respect to y. So we've got the minus 3 on 2, which is from here, which comes down the front. And then we need to do times the derivative of this thing, which is equal to 2 times y minus y prime. And then we've got the x minus x prime squared plus y minus y prime squared plus z minus z prime squared, and this is now to the 1 there, so minus 5 on 2. And then we've got this next one here, which again, the y minus y prime isn't a function of z, so we can bring that out the front. So now we've got minus y prime, and now we are differentiating everything in here, which is the same as what was in there, but now with respect to z. And that is going to end up the same way. So we'll end up with minus 3 on 2 times 2, but in this case it'll be z minus z prime. And then we'll have x minus x prime squared plus y minus y prime squared plus z minus z prime squared. And this will be to the minus 5 on 2 in this case. Now, you can see that this 2 will cancel that 2 will cancel that 2, but essentially we've got this out the front of this thing in this case, and this out the front of this thing in this case, and because we've got a z there and a z there, and the y there and the y there, these two terms are exactly the same, and so this is going to be equal to 0. And indeed, we could write out the same. We just did this here in the x direction, but we can do for y. It'll be d dz of this minus d dx of that, which will also be 0. And in the z, we'll have d dx of this minus d dy of this, which again will be 0. So that tells us that the cross product of r hat divided by r squared is equal to 0. And so we have this is 0 and we have this is 0. So that tells us everything inside the integral is 0. When we're integrating 0, we get 0. So this gives us that the divergence of B is equal to 0, which is what we were hoping to show. Now, Griffiths also gives a very formal explanation of how we can calculate the curl of B, though it does skip a few steps, like similar to in the divergence, this being 0 was included in one of the problem sets, and I've expanded every step here to show you why that came about. There's also a lot of steps within the proof for the curl that are in sections of the textbook that we haven't covered. So I think since we're physicists, let's just go with our more intuitive understanding of the curl of B that we came up with on this slide here, rather than working through everything. To work through, we took the curl of this thing, whereas when we were doing the divergence, we took the divergence with it, and then we have to make use of the product rules, much like we did over here, and then we needed to make use of a few mathematical facts that you work through in some of the problem set problems if we work through the whole of chapter 1. But let's just take it as given that the curl of the magnetic field is equal to mu naught times the volume current density. So the equation that we've been looking at for the curl of a magnetic field, which is equal to mu naught J, where J is the volume current density, is a form of Ampere's law. This is the differential form. You have seen the integral form before in Physics 1b. So to show how we can get from this differential form back to the integral form, we've already got from the integral form to the differential form, but let's go back the other way. We can write the curl of B is equal to mu naught J. And then we're going to do the same thing to both sides. So we're going to integrate both over dA. And what we can do with our left-hand side here is use Stokes' theorem. We've got the curl of a field over an area is equal to the integral over a closed loop of that field. So we can write that this is equal to B dot dl, and that's around a closed loop. And with our right-hand side here, we can pull mu naught out the front, and then we've got the integral of the volume current density over a surface, and it's the surface which is enclosed by this loop here. That's what our relationship in Stokes' law tells us. This is the loop that encloses this surface, so that must be obeyed here as well. And J dot dA, we know from before, is just equal to the current enclosed. So this is equal to mu naught I enclosed, and we've now got our integral form of Ampere's law that you are very familiar with from Physics 1A. So remember, this equation here doesn't give us the sign for the current or the magnetic field. We can choose this dl to be arbitrarily going like clockwise or anti-clockwise in order to get the relationship between the direction of the magnetic field and the current. You're going to need to use your right hand rule. Now, we've discussed when we were looking at the Biot-Savart law that it fulfills the role of Coulomb's law in electrostatics, but in magnetostatics. Well, in a similar way, we can say that Ampere's law fulfills a similar role to Gauss's law. So Ampere's And just as in electrostatics with Gauss's law, it's always true, is not always useful. So we applied Gauss's law to situations where there was a lot of symmetry, things like spheres and cylinders. And the same rule applies with Ampere's law. It's very useful in some situations, and those situations are where we've got a lot of symmetry that we can exploit. Then there's quite a lot of situations where it's not very useful at all. So it is useful for things like an infinite straight line, an infinite plane, infinite solenoid, or toroids. So we'll have a look at a couple of the examples now of where we can use this, but I do expect you to be familiar with a lot of examples from Physics 1B as well. So in this problem, we're asked to find the magnetic field of an infinite uniform surface current described by K is equal to Kx hat. So it's got the same magnitude everywhere and it's going in the x direction, flowing over the xy plane. So let's start by sketching out what is going on. If we draw our axes, here's our z-axis, here's our y-axis, and here's our x-axis. And let's just extend them a little bit. And we've got an infinite sheet in this at z equals 0. And it's got a current flowing in the x direction like this. And it's confined to this sheet here. So our first task is to work out how to draw the Amperian loop. For this, it's useful to refer to the Biot-Savart law for a surface current. So we've got B is equal to mu naught over 4 pi times the integral of K of R, well, this is R prime, cross R hat over R squared dA prime. So because this is a cross product between K, which is in the x direction, and R, we know that the magnetic field must be 0 in the x direction. So this tells us no B in x direction. And so this suggests that we would want our Amperian loop to be in the z and y directions, as those may not be 0. So let's draw an Amperian loop. Let's make it like this, and we'll let it have length L this way and a height H this way. And we're going to need to go around our loop in a certain direction. So it doesn't matter which way we choose the direction, because Ampere's law isn't good at telling us directions. We're going to have to use our right hand rule to get our directions and use Ampere's law to get the magnitude. Okay, so Ampere's law tells us that the integral around this loop of B dot dl is equal to mu naught I enclosed. And we can work out I enclosed because we've got a surface charge density. We've seen when we have a volume charge density that the enclosed current is equal to the integral over the surface of the volume current density dA. And similarly, if we have a surface charge density, we've got that the enclosed current is equal to the integral over a line of K dot dl. So with this one, if we picture this loop here, the current is coming out of the screen. So the amount of current contained is going to be equal to L times K. So this will be equal to KL. Okay, and now what we're going to need to do is think about, along here, we've got a y component. This length is going in the y direction. And on the two sides here, we've got a z component. So let's start by considering the z component of the magnetic field. Now, I think this felt fairly trivial to Griffiths. It doesn't feel that trivial to me, so I'm going to explain it in detail. But if you feel that it's trivial, then feel free to run it through on double speed or something. Okay, so when we're thinking about what's going on with the magnetic field in this Z direction, there's a few things that we should be aware of. Firstly, because this is an infinite plane of charge, it can't matter which point on the XY plane we're above. They should all look identical to each other. So should be independent of position on XY plane. So as an equation, what we mean by that is that the Z component of the magnetic field should be the same at X1, Y1, Z as at X2, Y2, Z for any X1, X2, Y1, Y2. And we've already said, I mean, this has to be true for X already from what we've said up here, that it's 0 in the X direction. Okay, so there's two ways that we can proceed from this, which both give us the right answer. So I'll just outline both of them to you, and you can use whichever one you want. Okay, first of all, if we consider, I'm drawing my loop here, and we're considering in the X direction, and this point here is at Z equals 0, and this point here is at, say, Y1, and this point here is at Y2. And we've just said that in the z direction, it needs to be independent of y. So we can argue that the magnetic field here is the same as the magnetic field here. But in this case, dl is going up, and in this case, dl is going down. So we can argue that this component must cancel out that component, and the same on the other side of the z-axis. This b must be equal to that b, and this one's, the L is going down, and here the L is going up, so they must cancel each other out. So can argue that as bz of y1 is equal to bz of y2, and L is opposite, must cancel. So that's one way that we can see that we don't need to consider the z components in this here, the dl, because they cancel out. Another argument is if we consider a point above, so let's consider a point there. So let's let this be at x, y, and z. And then we're going to consider another point down here at x, y, and minus z. Now, considering these 2 points and considering our Biot-Savart law, because the r vector points from where the current is, so let's consider the little increment right below this point. For this point up here, the r vector is this way, and for the point down here, the r vector is downwards like this. So this tells us that because the r vectors are in opposite directions, but this is in the same direction, the magnetic field must be in opposite directions at these 2 points. So if the magnetic field was pointing up at this point, it would have to be pointing down. So as an equation, we can write that the magnetic field in the z direction at z must be equal to negative the magnetic field in the z direction at minus z. So another argument that we can use to argue that this part doesn't contribute is that the part up here must cancel out with the part down here, because the magnetic field here has the opposite sign but same magnitude as the part out here. However, we could take this argument even further. We could think about what's going to happen to the magnetic field here if, say, for example, instead of going in the x direction, it started going in the y direction. Well, this going up here wasn't dependent upon this x direction at all. So changing the direction within this plane can't have an effect on the direction of B here. And if it doesn't matter if it's going in the y direction or the x direction, then imagine if we switched it from the x direction to the negative x direction. In that case, we flipped the sign of this thing, and this thing doesn't flip. And so the only way that can occur is if it is in fact 0 everywhere. So this implies that argument. So because it does not depend on direction of K in plane, BZ must be 0 everywhere. Okay, so you can use any of those three arguments to explain why the b dot dz component of this must be equal to 0. So this means that we only need to worry about the y component. So we've got that b dot dl. We only need to consider the y length now. So assuming that that the magnetic field is constant all along this loop, which it must be because of symmetry, because this is an infinite plane. So any y point needs to be the same. So we've got this is equal to b, and then we've got this length plus this length. So the total length is 2l. And we know that that is equal to mu naught I enclosed, and I enclosed is KL. So this is equal to mu naught times KL. And then you can see that these L's are going to cancel out. So this tells us that B is equal to mu naught K on 2. Now, it doesn't tell us anything about the direction. We know that the direction is in the y direction, but it doesn't tell us if the magnetic field is going to the right or going to the left. In order to work that out, we'll need to use our right-hand rule. So if you point your right thumb in the direction of the current, then your fingers wrap around and show the direction of the magnetic field lines. So doing that, up above here, the magnetic field lines must be going this way, and down below, they must be going this way. So we can say that B is equal to, this is in the negative y direction. For z is greater than 0, that's above our axis, and it's equal to mu naught k on 2y for z is less than 0. So in this example problem, we're told that a toroidal coil consists of a circular ring around which a long wire is wrapped, as in this figure here. The winding is uniform and tight enough so that each turn can be considered a closed loop. Show that the magnetic field is circumferential, which means it's going around the circumference at all points inside and outside the coil. Hence, determine B, the magnetic field. Okay, so this problem is to do with currents and magnetic fields, but it is reminiscent of this problem which we solved for electric fields, where we had a charge distribution around a ring and we were considering the electric field above the ring. And in this case, we exploited symmetry by considering points on opposite sides of the ring. So we are going to end up employing a similar technique in order to solve this magnetostatic problem. So a good way to start this problem is to really clearly define our coordinate system. So let's choose our z-axis, which is going up through the middle of our toroid, and we'll choose our y-axis this way. So the bottom of the toroid here is at z equals 0, and the top of the toroid here is whatever this height of our torus is, and we will let our x-axis be coming out of the screen towards us like this. Okay, and we'll just dot on the negative axes as well in case they're useful. Now, what we're going to do is choose some point in the xz plane, so with y equals 0. Let's choose that point here, and this is at height z, and it's at distance x, and it's at y equals 0. So we can call this point R, which is where we're going to measure that magnetic field, and R is equal to x, 0, z. Now we're going to use the Biot-Savart law, and the Biot-Savart law tells us that the magnetic field due to a little increment is given by mu naught over 4 pi I cross curly r over r cubed. So usually we write this as r hat here with an r squared here, but in this case I've written this as curly r divided by r cubed. That those are the same thing times the length of the little increment that we're considering. So in order to calculate this for any little point, we'll need to consider one little point in particular. It can be anywhere, and then we'll try and generalize what we learn from that little point. So let's choose a little element of current here, and we'll let this little element be at r prime. Now, because the toroid has circular symmetry, it's easier to really say where this is in cylindrical coordinates. So let's say that this is our radius s prime, and the angle it makes with the x-axis here is phi prime, and it's a height z prime above the base of the z-axis like that. So we can write down, we'll want to write it down in Cartesian coordinates, even though we've defined where it is in cylindrical coordinates. So in cylindrical, r prime is at s prime, and then it's phi prime and z prime. But because we've got r over here in Cartesian coordinates, we're going to want to convert from our cylindrical coordinates into our Cartesian coordinates. So this is going to be given by s prime cos phi prime, s prime sine phi prime, z prime. And then in this equation, what we need is this curly r. And remember, curly r is equal to the vector pointing from here to here. Let's draw that on. Let's grab another color. This is curly r. And so we can say, well, curly r is equal to r minus r prime, which is equal to x minus s prime cos phi prime minus s prime sine phi prime, z minus z prime. Now, we've considered curly r now. Now we're going to need to consider the current. So in a toroid, we're told that the windings are uniform and tight enough so that each turn can be considered a closed loop. So what that means in practice is that on each of these loops, the current is flowing, here it's flowing upwards, so in cylindrical components that's in the z direction, and then along here it's flowing in the radial direction, so in the s direction, but nowhere is the actual turn going around the circle like this. So the current is in the radial or the vertical direction, not in the phi direction. So that tells us, we're running out of colors, let's go with purple for the current. So current is in S and Z direction. So we can write that the current I is equal to IS S hat plus IZ Z hat. And so if we want to write this in Cartesian coordinates, we can write I is equal to IS cos phi prime, IS sine phi prime, and in the Z direction it's IZ. I should have put a little squiggle under that as well because that is also a vector. Okay, so now we have written down expressions for all our vectors in this equation. So this is the hard part of the equation, the cross product part. So what we're going to do now is work out what that cross product is. So we can write, well, I cross R is going to be equal to, we've got in the x direction, I is given by is cos phi dash, and R is, this is curly R, is given by x minus s prime cos phi prime. In the y direction, we've got is sine phi prime and minus s prime sine phi prime. And in the z direction, we've got iz and z minus z prime. Okay, so we can work out what this is. So we've got in the x direction, is, well, let's put it as z minus z prime. And then we've got is sine phi prime minus, but we're doing minus this times this, and there's a negative sign here. So those negative signs will cancel out, and we'll end up with a positive. And this will be s prime iz sine phi prime. So that's our x direction. In our y direction, we've got this times this minus this times this. So that is iz outside of x minus s dash cos phi prime minus z minus z prime times is cos phi prime. And then in the z direction, we have got this times this minus this times this. So this is going to be equal to minus is s prime cos phi prime sine phi prime minus is sine phi prime times x minus s prime cos prime. Okay, so now we've written that down. What we did in the electric case was we exploited the symmetry, and we are going to do the same thing in this case. So in order to see how we can exploit the symmetry, what I'm going to do is write this x prime term as sine phi dash times whatever's left, but you can see that there's a sine phi prime in every term here. So we can write this as z minus z prime is plus s prime iz. Now in the y prime, the y direction, there is no sine term in every term. So we can't do a similar thing in the y direction. So the y direction one is more complicated, and we'll just leave it as it is. So iz x minus s prime cos phi prime minus minus z prime times is cos phi prime. And then in the z direction, once again, you can see that there's a sine phi pri term in factor in every term. So we can pull that out the front. I mean, we could pull the is out the front if we wanted as well, but it's not necessary. So we can write this as sine phi prime. Let's pull the is out the front. and this is minus s prime cos phi prime minus, I can pull the minus out the front as well. Let's pull the minus out the front. That'll make everything a bit neater. Let's put that as minus, and then this becomes plus, this becomes plus, and we've got x minus s prime cos phi prime. And these two cancel each other out, so it actually ends up neater. We can write this term here. I can't be bothered writing the other two terms out again, so I'm just going to rewrite this term as in the z direction. We've got sine phi prime is x. Okay, and now comes the sneaky part where we exploit the geometry. So we chose this point here at an angle phi prime. What we can do is choose another point on the opposite side of the toroid at an angle minus phi prime. So let's choose, let's go with dark green. So let's choose this one, which is minus phi prime, and then we're going to have everything else the same. So let's call this one r double prime. So this is r double prime, and it is at s prime minus phi prime z prime. So everything else is the same apart from phi being opposite. And if we consider how much this contributes at this same point here, sorry, my drawing's a little bit squiffy, but this point here is midway between these 2 points because it's at y equals 0. And so the length for our curly r vector from each of these is going to be the same. So everything is going to be the same apart from this angle. So when we look at these terms, we know that sine of phi is equal to negative sine of negative phi. So when we sum up this term plus this term, the sine components, which is why I pulled the signs out separately, are going to have opposite signs, but nothing else has changed. X is the same, is the same, z's the same. So everything else is the same apart from the sign in front of our sine terms. So the x term and the z term are going to cancel each other out. On the other hand, the y term, we don't get that cancellation because we've got cos phi prime, and cos of negative phi is the same as cos of phi. So those ones don't cancel out. So this tells us that the x and z components cancel, and we are left with y. So at this point here, which I've drawn badly, the magnetic field dB is the only contribution that we have to worry about when we consider the sum from this point and this point is in that horizontal y direction. And notice how that is in the phi direction, because phi is always a tangent to this circle around here. So it turns out that it doesn't matter which point we consider. We can always choose 2 points where the magnetic field cancels out in all directions apart from our phi direction. And we were asked to show that this is circumferential at all points, and so that is how we show it. So the x and y components cancel out, and we're left with y. At our chosen point, y is the y direction is equal to the phi direction. and in general, it is always in the phi direction, and hence circumferential. Okay, so now we've done the hard part. Now we can do the easy part, hence determine B. So to do that part, we are going to have to take an Amperian loop. Let's draw our Amperian loop in lavender. So we'll take this inside the toroid somewhere like that. It's a circle, and we'll let it have a radius S. In this case, we can use Ampere's law. I'll switch to dark purple to write down that B dot dl is equal to mu naught I enclosed. Now, the I enclosed is going to be equal to the number of turns that we've got times I. And B and dl, we need to take that circumferential direction there. And so B, if we assume B's constant around that circle, which should be centered in the middle of the torus, mine's drawn a bit squiffy, and then the integral of dl is just the circumference, so that'll be 2 pi r, and this is equal to mu naught ni. So that tells me that B is equal to mu naught ni divided by 2 pi r. Now, as long as I take my loop symmetrically, so it's in the middle somewhere there, I can assume that my magnetic field is constant around that loop. And then the integral around the loop of dl is just the length of the loop, which is the circumference, which is 2 pi s. And that is equal to mu naught ni. So that tells me that B is equal to mu naught ni divided by 2 pi s. And this is in the circumferential direction, so I can write times that phi vector there. And this is inside the coil. Now, if I imagine taking a smaller loop like that, then I've got 0 enclosed current. So this part here is 0. So it's going to be 0 like in the middle of the toroid. Or if I imagine taking a loop at a much greater radius outside like this, then I've got the current flowing up here, and I've got the current flowing down there. So each of those currents is going to cancel each other out. And so again, I've got 0 enclosed current. And so we can say that this is equal to 0 outside the coil. So before we move on, it's very useful to point out the parallels between magnetostatics and electrostatics. So for electrostatics, we can write down that the divergence of the electric field is equal to 1 over epsilon naught times rho, which was Gauss's law. So it's no surprise when we consider what electric fields look like for a positive charge like this, they're all exploding or diverging away from a point, that we've got this formula here for divergence. And the curl of the electric field is 0. You can see there's nothing which is making this swirl around the origin. On the other hand, for magnetostatics, we've got that the divergence is 0 and that the curl is equal to mu naught J, where J is the volume current density. And this is known as Ampere's law. And again, just thinking back to the geometry, if we've got a current coming out of the screen, then we know that the magnetic field lines curl around that current like that. So the fact that this is 0 and this part is not 0 is not really surprising. So these combined are Maxwell's equations. So these ones Maxwell's equations for electrostatics. These ones are Maxwell's equations for magnetostatics. And these equations for electric fields, along with our boundary conditions, assuming that E goes to 0 as we get an infinite distance away from a charge, let us determine the field as long as we're given this charge density here. So these contain all the information that is given in Coulomb's law, along with the law of superposition. And similarly, for the magnetostatic equations, as long as we assume that B goes to 0 as we get a long way away from the charge, then these equations tell us all about the magnetic field, given that we know the volume current density. And so these contain equivalent information to the Biot-Savart law with the law of superposition. So Maxwell's equations, along with our force law, which is F is equal to Q E plus V cross B, basically allow us to get everything that we've gotten so far. Now, another point of comparison between these two is that the electric fields and electric forces tend to be much larger than the magnetic fields and the magnetic forces. The only reason that we can really feel the magnetic forces is when the current density gets really high, so there is an awful lot of current flowing, or alternatively if the charges start to move really fast, so getting close to the speed of light. In that case, they are going to start contributing a lot more as well. And as far as we know, there are no magnetic monopoles, so we can't have a single magnetic charge like this with a divergence. That's what this says. Though there are a few theories that kind of require it, but nobody's found one yet, so they're definitely not easy to find if they do exist. Okay, as we move on, we'll be looking at more similarities between the magnetostatic and the electrostatic case.